Okay, so let's see this. It says if f is continuous and non-negative on the closed interval AB, then the region of the area bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is the integral from a to b f of x dx. So what it's saying is this interval right here, the definite integral, represents the area if and only if everything's above the axis. If it's not above the axis, then what you have is this positive area, this quote-unquote negative area that you're putting together. So it's not going to represent the total actual area. It gives us some direction with where the area is. So let's look at these to try to start seeing these next few ones, to try to start seeing if we can figure out some rules here to help us with definite integration. So the first one says find the integral from 1 to 3 of 4 with respect to x. So let's think about what the graph of this looks like. Y equals 4 is a horizontal line. So this would be y equals 4. And what we care about is we care about from x equals 1 to x equals 3. And we want to find that area in there. Well, if we look at that area in there, that actually forms a rectangle. So let's think about the sides of this rectangle. What would the height of this rectangle be? Well, the height would be 4. And what would the width be? Well, it would be 3 minus 1, which is 2. So if I wanted to find the area of this shape, I would do 4, the height, times 2, the width, and that would give me 8 units. So the area of this would be 8 square units, whatever the units are. Let's look at this next one. Let's consider the function x plus 2 on the interval from 0 to 3. So what's x plus 2 look like? It's just a horizontal or a diagonal line, right? It starts off with the point, if we plug in a 0, that would be the point 0, 2. And this is at x equals 0. And then we could go out to x equals 3, and if we plug in a 3, 3 plus 2 would be 5. So that would be the point 3, 5. Okay? So what's the idea? We need to find the area of this piece right here. Well, how do you want to find the area of that? That's kind of up to you. It does create a trapezoid if you know how to find the area of a trapezoid. Or what I would like to do most likely is break it into a triangle plus a rectangle. So that's probably what I'll do to think about the height of the rectangle. The height of that rectangle would be 2. The width of it would be 3. So the area of the rectangle would be 2 times 3, which is 6 square units. That triangle, again, this side is 3. And then the height would be 5 minus the 2, which is also a 3. So the area of the triangle would be 1/2 times the base, which is 3, times the height, which is 3. So that would be what, 9/2? So the total area, which is what, 4.5? Okay, so the total would be the sum of the two of those numbers, and that would give us 10.5. Again, we could have gotten that same number had we used a trapezoid and found the area of a trapezoid, which is 1/2 times the sum of the bases times the height, but I'm not going to mess with that with you guys. I just broke it into two figures that I easily knew. So let's look at this next one right here. We're looking on the interval from -2 to 2 of the square root of 4 minus x squared. I'm going to think about the graph of this and see what this looks like. So if I plug in a 0, the square root of 4 is 2, so the point would be 0, 2. If I plug in a 1, it'd be 4, or let's plug in a 2. How about that? Because a 2 is a nice number. If I plug in 2, it would be 2 squared, so 4 minus 2 squared is 0, square root of 0 is 0. If I plug in a -2, I'd actually get the same thing. So what are we dealing with as a shape here? We're dealing with half of a circle. That circle has a radius equal to 2. So to find the area of this, it's going to be half of a circle. So that's going to be half of the area of a circle is pi times the radius, which is 2 squared. So in this case, it would be 4 pi over 2, or 2 pi would be the area of half of the circle. So this area right here would be equal to 2 pi. So the question then becomes, is there a way that we could find the answer to this without having to integrate or find the area of those geometric shapes that we knew, right? The whole entire point of the last section was we no longer have to use triangles, rectangles, circles. We don't have to find the area of those shapes, because what we can do is find the area of small rectangles and do an infinite number of them. So, but if we use the limit process on these problems, especially this last problem, that would be an absolute miserable process. So sometimes the limit process is the best thing to do, and sometimes it's absolutely not the best thing to do. Sometimes you just want to look at the picture and see if you could figure out exactly what it is without using the limit process.